Hello everyone, in this video we'll be solving HL paper 1 question for IB Physics topic 5, electricity and magnesium. So before solving problem, I would like to clarify some issue we have for the SL paper 1. So here there are two images that showing different way that we'll be using in identifying the direction of force, current, and other quantities. So here, this is the left-hand rule, and this is the right-hand rule. So eventually, those two will give us the same answer, right? And in the SL paper, I use the right-hand rule. In HL paper, I will be using the left-hand rule just to show you two different way of solving a problem. And when you are when you see the current and you want to know the direction of magnetic field, or you see the direction of magnetic field and you want to know the direction of current, this is the method we often use, using your right hand. So now I will be solving the problem to show you different way. A cell of electromotive force 6.0 volt and negligible internal resistance is connected to three resistors as shown. The resistors have resistance of 3 ohm and 6 ohm as shown. What is the current in resistor X? So here is resistor X, and here is current I. So we know that the total current passing through resistor X is equal to the total current in the circuit, right? So here will be as I sum. And total current is equal to electromotive force divided by the sum of resistance in the circuit. So in this problem, you just need to solve for total resistance in the circuit. So how do we do this? The first thing we see is that you have two resistors connected in parallel. So I'm gonna solve for this resistance here, right? So we know for resistor connected in parallel, their resistance, so I'm gonna call this resistance in parallel, R sub P, is gonna be equal to 1 over 6 plus 1 over 6. And this tells us resistance in parallel is equal to 3 ohm. And now the circuit is simplified to this. So let me draw another diagram. So here is resistance X, and here the two resistors connected in parallel has a resistance of 3 ohm. Right. And here the two resistors are connected in parallel, and they have a sum resistance of 6 ohm, because 3 plus 3 is equal to 0. 3 plus 3 is equal to 6. So now we can solve for total current, which is equal to electromotive force 6.0 volt divided by the sum of resistance, which is 6 ohm, and this is equal to 1 ampere. So the answer will be C. Oh, just a trick. If you have resistance connected in parallel and each resistor has equal resistance, then the resistance in parallel is equal to the resistance of one resistor divided by the total number of resistance in parallel. For instance, here both resistor has a resistance of 6 ohm, so their sum resistance in parallel is gonna be equal to 6 divided by the total number of resistor, which is 2, and this will also give you an answer of 3. So this is just a trick of solving problems. A lamp and a semiconducting diode have the voltage current characteristics shown and are connected in parallel. What is the resistance of the lamp and the resistance of the diode when the current of each device is 2.0 ampere? So how do we solve this problem? So we know that they are connected in parallel, which means that each device has the same voltage. Each device has the same voltage. I'm just gonna write volt. And they have same voltage here, which is 1. Right? And now we can solve for resistance. So resistance is equal to voltage divided by current, which is equal to 1 divided by 2 ohm. And this is equal to 0.5 ohm. So the answer will be D. 4-point charges of magnitudes positive Q, negative Q's, and negative Q's are held in place at the corners of a square of set R. The Coulomb constant is K. Which of the following is the electrical potential at the center of the square O? So since it's a square, we know that distance here will be equal to distance here, will be equal to distance here, will be equal to distance here. And for simplicity, I'm just gonna represent the distance using the variable x. So let me write this down. Here is x. And now we can solve for electrical potential. So because here is positive Q, electric potential will be equal to Coulomb constant multiplied by charge divided by distance, which is x. And here is negative Q, so it will be equal to Coulomb constant multiplied by charge, which is negative Q. So here will be a negative sign divided by distance x. And here will be KQ divided by x. Here will be equal to negative KQ divided by x. So the sum will be equal to KQ divided by x plus KQ divided by x minus, when I say minus because here is a negative sign, KQ divided by x, and here is another negative sign here, and this will be equal to 0. So the answer is 0, right? Just another trick. Right? When you see potential or electric potential, if you have a positive charge here and negative charge here, and they're equal distance, you should immediately know the electric potential is equal to 0 because they cancel out by the positive and negative charge. But the electric field is different because positive charge will radiate outward and negative charge radiate inward. So electric field does not equal to 0. So these are just some tricks. When you see a positive charge and negative charge and they're equal distance away from a point, you should know that electric potential is equal to 0 at the point where distance are equal. When an electric cell of negligible internal resistance is connected to a resistor of 4R, the power dissipated in the resistor is P. What is the power dissipated in the resistor value R when it is connected to the same cell? So connected to the same cell means they have the same voltage, and power is equal to current square multiplied by R. This is also equal to voltage square divided by R, and this is also equal to voltage multiplied by current. So R is changed. R has changed from 4R to R, meaning that resistance has been divided by 4. As a result, the power will be multiplied by 4, right? So the answer will be C. And if you don't see why, I can solve this step by step. So initially, 4R is equal to P, right? V squared divided by 4R is equal to P. And now it becomes R squared divided by R. And this is equal to this thing here. So it will be 4P. A circuit is formed by connecting a resistor between the terminal of a battery of electromotive force 6 volt. The battery has internal resistance. Which statement is correct for 1 coulomb of charge flows around the complete circuit? 6 volt is the potential difference across the resistor, so this is wrong. It should be the potential difference across the terminal, or you can say the complete circuit. 6 volt is the thermal energy dissipated in the cell. This is also wrong. It's not thermal energy. 6 volt of chemical energy is transformed in the battery, so this is correct. This is about energy transformation in the cell. Chemical energy is converted to electrical energy. Oops. 6 volt of thermal energy is dissipated in the resistor. So this statement is completely wrong. First of all, is not thermal energy. Secondly, is not really about resistors. So here, D is wrong. A ion of charge positive Q moves vertically upwards through a small distance x in a uniform vertical electric field. The electric field has a strength E, and its direction is shown in the diagram. What is the electric potential difference between the initial and final position of the ion? So we know that potential difference is equal to electric field multiplied by change in distance when the strength of the field remain uniform. And here we know that the strength is just E, and moving through a distance of S. So is equal to E multiplied by S. So the answer will be C. A 12 volt battery has an internal resistance of 2 ohm. A load of variable resistance is connected across the battery and adjusted to have resistance equal to that of the internal resistance of the battery. Which statement is correct for the circuit? So here, A says the current in the battery is equal to 6 volt. So how do we do this problem? I recommend to draw a diagram. So here you have 12 volt battery, which has an internal resistance of 2 ohm. A load of variable resistance is connected across the battery and has equal resistance to the internal resistance. Here another resistor which also has a resistance of 2 ohm. And the first one says the battery is equal to 6 ampere. So current is equal to electromotive force divided by resistance. And here it's gonna be equal to 12 volt divided by the sum of resistance, which is equal to 2 plus 2 is equal to 4. So the answer will be 3 ampere. So the first one is wrong. The potential difference across the load is 12 volt. This is also wrong because you know that there should be a potential difference across the internal resistance. So here the potential difference across the low resistor cannot be 12 volt, and here should be 6 volt. 6 volt here, 6 volt here. You can also calculate that because you know the current here is equal to 3, and here has a resistance of 2, so here is equal to 6. So B is also wrong. The power dissipated in the cell is equal to 18 watts. So power is equal to voltage squared divided by resistance, which is equal to 12 squared divided by 4. So 144 divided by 4, which is equal to 18. So C is correct. The resistance in the circuit is equal to 1 ohm. You definitely know this is not correct because they're connected in series. So R is equal to 4 ohm. A proton P is at rest between the poles of two horizontal magnets as shown below. The magnetic force on the proton is Y. So here you need to know how to use left-hand rule. So between two magnets, the magnetic field will point from the northern pole to the southern pole. And you need to know this in order to solve the problem, right? So this is the direction of magnetic field. A proton is at rest. What is the magnetic force direction? Because the proton is at rest, we know that the magnetic force on the proton must be equal to 0, right? And I know this sounds a little bit tricky. So here is how we solve it. Because proton is a particle, we don't consider gravity, and we assume that gravitational force on particle is equal to 0. This is because their mass is too small that we can ignore the impact of gravitational force on particle. So here, if there is no downward force, we won't want any other forces, right? Because we want the net force to be equal to 0, so the proton can be at rest. And this is from Newton's first law, I think. So in order to not having any forces, the magnetic force also needs to be equal to 0. So the answer will be D. The diagram shows the path of a particle in a region of uniform magnetic field. The magnetic field is directed into the plane of the page. The particle should be Y. So this is a very classic problem, and how you solve it is very simple. So assuming the particle is here, we know that is in circular motion. Which means that centripetal force points to the center. So here, the force will be in this direction, right? And we also know the direction of magnetic field, which is pointing into the page, points into the page. And now using left-hand rule, you can solve for the direction of current. Or so make sure your thumb is pointing upward, and your second finger should point into the page because it represents the direction of magnetic field. And the other 3 fingers represent the direction of current, which points rightward. So here will be the direction of current here, right? And for circular motion, you know that velocity is always tangent to radius and is supposed to point to this direction. So from this, we know that it gotta be a positive charge particle. It gotta be a positive charge particle because the direction of current here is in the same direction with velocity. So it gotta be a positive charge particle. And here a photon has no charge. A neutron has no charge. a beta particle, no, this is not correct. An alpha particle is correct because a alpha particle is equal to 2 protons, helium. So the answer will be A. Just a reminder here, if the direction here, if in any direction, if in any similar problems, current is in the opposite direction with velocity, you should know that it will be a negatively charged particle. A current carrying wire is in the same plane as a uniform magnetic field. The angle between the wire and the magnetic field is theta. The magnetic force on the current carrying wire is what? So here you also need to use the left-hand rule. So let's see how we can solve the problem. So here is the direction of current, and here is magnetic field. So using left-hand rule, your second finger should point to the right direction. So point rightward, and then your current. So the other three fingers should align with the direction of current, which is here. So here should be your 3 fingers. And here will be your second finger. Right. And your thumb will be the direction of force, which will point inward into the page. So here, B is the answer. So this problem is also about using left-hand rule. By the way, when I say the second finger, I mean index finger. Index finger is equal to the second finger in my sentences and previous problem when explaining the left-hand rule. And I apologize for the confusion. Electrons, each with a charge E, move with speed v along a metal wire. The electric current in the wire is I. Plane P is perpendicular to the wire. How many electrons pass through plane P in each second? So we know charge is equal to current multiplied by time. And in this case, each second means time is equal to 1 second. Right? And we also know that charge here is equal to n, number of electron, multiplied by the charge of electron. So n is equal to n multiplied by the charge of electron is just equal to I, since T is equal to 1. Therefore, n will be equal to I divided by the charge of an electron. In this problem, the charge of electron is represented by the letter E. So the answer will be D. A ion follows a circular path in a uniform magnetic field, which single decreases the radius of the path. So in circular motion, magnetic force is equal to centripetal force, which means that Q, charge multiplied by magnetic field multiplied by velocity, sine theta is equal to 1 because theta is equal to 90 degrees. So I'm not going to write sine theta here, is equal to centripetal force, which is equal to mass multiplied by velocity squared divided by r. So radius will be equal to mass multiplied by velocity divided by charge multiplied by magnetic field. So if you want to decrease the radius of the path, you can either decrease mass and velocity, or increase charge or magnetic field. So here, increasing the mass of the ion will increase the radius. Increasing the charge of the ion will decrease the radius. Increasing the speed of the ion will increase the radius. Decreasing the magnetic flux, which means decreasing B here, will increase the radius. So the answer will be B. A resistor has a resistance R. The potential difference across the resistor is V. Which of the following gives the energy dissipated in the resistor in time t? So here we need to solve for energy dissipated. So we know that energy dissipated is equal to power multiplied by T. And power is equal to V squared divided by R multiplied by T here. So this will give us an answer of D, right? So in order to solve those problems in a short period of time, you need to be very familiar with all formulas. So power is equal to voltage multiplied by current, which is equal to current squared multiplied by R, which is equal to V squared divided by R. So you need to know all those formulas, right? The electric potential V is V sub R at a point R in the electric field, and at the another point S, the electric potential is V sub S. Which of the following is the work done by the electric field on a point charge positive Q as it moves from R to S? So we know that work done is equal to negative change in potential energy. And we also know that work done is just equal to change in kinetic energy, right? So change in potential energy here is gonna be equal to negative work done. And work done using electric potential is just equal to charge multiplied by change in electric potential. So here will be equal to charge, here is positive charge multiplied by change in potential. So it moved from R to S. So final electric potential at S is Vs. And initial electric potential at R is equal to VR. And then you have a negative charge here. And this will be equal to Q multiplied by V sub R minus V sub S, right? So you reverse change in potential, which eliminates the negative charge in front. So the answer will be D, right? So the key thing here is about this. Potential difference is equal to negative work done. This is very important and frequently tested in paper 1 questions. Two wires X and Y are made from the same metal. The wires are connected in series. The radius X is twice the radius that of Y. The carrier drift velocity in X is Vx, and in Y is Vy. What is the value of the ratio V sub X divided by V sub Y? So because two currents are connected in same series, you know that they have same current, right? So Ix is equal to Iy is equal to I. So we need to know their drift velocity potential. We also know their radius ratio, right? So because the radius of X is twice the radius of Y, we can say that the radius, the area of Y is A, and the area of X is 4A, right? And current is equal to number of electron multiplied by the charge of a electron multiplied by A multiplied by V, right? So let's say current in wire X. So current in wire X is gonna be equal to N multiplied by E multiplied by their area, which is 4A, multiplied by Vx, and is equal to current in wire Y, which is equal to N multiplied by E multiplied by area A multiplied by Vy, right? And here cancels out. So 4Vx is gonna be equal to Vy, which tells us that Vx divided by Vy is gonna be equal to 1/4 is equal to 0.25. So the answer will be A, right? So this is the answer here. So let me move this upward a little bit. A Cooper wire with length L and radius R has a resistance R. What is the radius of a Cooper with length L over 2 and resistance R? Resistance is equal to resistivity multiplied by L divided by area. Because length is divided by 2. L is divided by 2. Area needs to be divided by 2 to have the same resistance R. And this tells us that R squared, radius squared, is divided by 2. Radius square needs to be divided by 2 to have a area of A divided by 2, right? And here is gonna be equal to 4A because R squared is equal to 4R squared, and here will give us 2A. Here will give us A over 2. And here will give us A over 4. So the answer is C. Positive charge is uniformly distributed in a semicircular plastic rod. What is the direction of the electrofield strings at point S? So here, positive charge is here. And we know that positive charge radiates outward. And we want to know the electrofield strings at point X. So here, let's say this point here, we'll have an electrofield in this direction. And here we'll have the electrofield in this direction. Here we'll have another electrofield direction, this direction, and electrofield in this direction, right? So from here, you should see that electrofield, they cancels out in those 2 points. So electrofield cancels out in those 2 points. And when I say cancels out, I mean the vertical component of electrofield cancels out, and it only has horizontal component. So the answer will be B. Here will be the not electrofield. And if you still don't see why, let me draw another diagram just to clarify things. So they have same distance here. And this is an electrofield here. E. So I'm gonna make it into a vertical component and horizontal component. And the horizontal component here and here, they cancel out, which only gives me the horizontal component here, right? So this is the direction represented by B. So B is the answer. Two resistors of resistance R1 and R2 are connected in series with a cell of electromotive force ellipson and negligible internal resistance, which expression gives the potential difference across the resistor of resistance R1. So how do we solve this problem? So we know that potential difference at resistor R1 is just equal to current multiplied by resistance, right? And we just need to solve for the total current here. And we know that total current is equal to electromotive force divided by the sum of resistance. And then you multiply by R1 to get the potential difference across resistor R1. And because both resistors are connected in series, our sum is equal to R1 plus R2. So this will be equal to electromotive force divided by R1 plus R2 multiplied by R1. And the answer will, and this is equal to which answer here? A, I think. Yeah, this is equal to A, right? So R1 plus R2 multiplied by electromotive force. So the answer is A. A voltmeter of resistance 50 kiloohm is used to measure the electric potential difference in a circuit as shown. The cell has an electromotive force of 5.0 volt and negligible internal resistance. What is the reading on the voltmeter? So here, what is the reading here? So this is a very important information here. The voltmeter actually has a resistance. So here you can draw a resistor here, 50 kilo ohm. Right. And now you just need to solve for the potential difference here. Potential difference here. So how do we solve for this problem? So the potential here, V is gonna be equal to current multiplied by resistance. And what is the current across here? So here, we need to solve for the total resistance here. So let's solve for total resistance here. So here, because they're in parallel, and each resistor has an equal resistance of 50 ohm, we know that the sum of resistance in this parallel circuit here is just equal to 50 divided by 2, which is equal to 25 kilo ohm. So the sum of resistance in this circuit is gonna be equal to 100 plus 25 kilo ohm. This is equal to 125 kilo ohm, right? And now we can solve for total current. So total current here is just equal to electromotive force divided by 125. And here, this is the current I sum. When it goes from here gonna have a current I, and here will also have a current I. So multiply by 1/2, and then multiply by 50 will give you the electric potential reading on the voltmeter. So this is gonna be equal to here will be equal to 250 divided by 125 multiplied by a half. This is equal to 2 multiplied by 1/2. And this is equal to 1. So the trick here is you need to read the question carefully because the voltmeter has no resistance. And this is very unusual in most cases. But when you are solving the problem, just make sure you label all information on the diagram. So the answer will be A. The problem here are repetitive. A positive charged particle follow a circular path as shown below. Which of following electric field could have caused the charged particle to have the above path? So here you just need to know this. So you know that they have a circular motion. They are in circular motion, which means that centripetal force point to the center. Centripetal force point to the center. And you should know that force is equal to charge multiplied by electric field. And because it is a positive charge particle, direction, velocity should be in the same direction with electric field. And this just tells you that electric field, E field, point to the center, right? And I think I said something wrong in my previous sentence. Because it's a positive charge particle, force is in the same direction, not velocity. Force is in the same direction with electric field, right? So E field must point to the center, and A is the only answer that point to the center. A metal rod is falling vertically within a horizontal magnetic field. The metal rod and magnetic field are directed into the page. So magnetic field is into the page. What is the direction of the initial force acting on the metal rod that is predicted by Lenz's law? If you haven't studied topic 11, just skip this problem. If you have, you can definitely do this problem. So Lenz's law says that a induced voltage will be a induced magnetic field will be produced to oppose changes in magnetic flux, right? And here, because it's pointing into the page, the magnetic field is pointing into the page, and when the object is traveling downward, right, is falling vertically within the horizontal magnetic field, the magnetic field here, the magnetic field experienced by the metal rod increases. Thus, the induced magnetic field will point out of the page to oppose the change. So from this one, you should know that the answer will be B. So how do I know the answer is B? Here's the trick. Because it will bring a change in magnetic flux, we know that it's gonna oppose this motion. It doesn't want the charge to falling vertically downward, so to change the magnetic flux. And in order to oppose the change of traveling vertically downward, they gotta have a force pointing upward to oppose this change. Because currently the metal rod is falling vertically downward. So in order to oppose the change, the force needs to point upward, right? Because they are in the opposite direction. And this is how you can solve this problem. In fact, you don't even need to care about magnetic fields here. just know that Lenz's law says there will be an induced magnetoflux or magnetoforce to oppose the change. And because here is traveling downward, there's gonna be a force pointing in the opposite direction to oppose the change. A circuit consists of a cell of electromotive force 0.6 volt and knowledgeable internal resistance connected to two resistors of 4.0 ohm. The emitter has resistance equal to 1 ohm, and the voltmeter is ideal. What are the rating of the emitter and the voltmeter? So how do we do this problem? So here, emitter raise the total current in the circuit, which is equal to electromotive force divided by total resistance. And here, because they are in parallel and each resistor has a equal resistance of 4 ohm, we know that the resistance in parallel is going to be equal to 4.0 divided by 2, right? The total number of resistors, which is equal to 2 ohm. So I sum here will be equal to 6 divided by 2 ampere, which is equal to 3 ampere. Is this correct? Oh, sorry. The emitter also has a resistance of 1 ohm. Yeah, the emitter also has a resistance of 1 ohm. So here, emitter has a resistance of 1 ohm. I'm just gonna draw another resistor here. Right. So our sum is equal to electromotive force, which is equal to 6.0 volt divided by the sum of resistance, which is equal to 2 ohm plus 1 ohm. This is equal to 6.0 volt divided by 3 ohm, and this is equal to 2 ampere. So you immediately know that B and D are wrong. And now you just need to know the rating on the voltmeter. So we know that the sum total current is 2 ohm, right? The total current is 2 ohm. And here has a resistance of 2 ohm. So let me simplify this circuit diagram just to make it more clear. Here is 1 ohm, here is 2 ohm, and here has a potential meter. So the potential difference here is what? So we know that current is equal to 2 ampere. So the potential difference here, V here, is equal to 2 ohm multiplied by 2 ampere. Current multiplied by resistance give you potential difference, which is 4 volt here. So the answer will be C. Two isolated point charges, -7 microcoulomb and +2 microcoulomb, are at a fixed distance apart, at which point is it possible for the electric field strength to be 0? So the first thing we need to know is electric fields of a negative charge radius inward, and electric fields of a positive charge radius outward, right? So here, let's consider the distance between A and B. Electric field by the positive charge radius outward, so it will be this direction. Electric field by negative charge radius inward, which will be this direction. So here is by negative charge and here is by positive charge. However, because the charge here, -7 microcoulomb, the absolute value of this charge here is greater than 2 microcoulomb, and B is also closer to any point between A and B, we know that the electric field by the negative charge will definitely be greater than electric field by the positive charge, right? So the magnitude. And how I get this conclusion is that electric field is equal to Coulomb constant multiplied by test charge divided by radius square. So our radius, not radius square, distance square. So any distance between A and B is not possible. What about distance between B and C? So let's say here has the charge. So the electric field by the negative charge radius inward, which will be this direction, electric field by the positive charge radius outward, which is also this direction. So let me use different color. So by the negative charge radius inward in this direction, and by the positive charge will radiate outward, which is also in the same direction. So both electric field points to the same direction, points leftward. So then that electric field cannot be equal to 0. What about any point between C and D? So we know that electric field by the positive charge point outward, so right direction, point rightward, by the negative charge will point leftward, right? Because it radius inward. And here, we know that the distance here, the negative charge, the distance between the negative charge and any point between C and B are farther away from any distance, from the distance between C and D to the positive direction. So this position here is possible. So, and which point is possible? You need to just select a position between C and D, right? So a position between C and D is possible. Let me give a better explanation here. C and D. This is B, and here has 2 microcoulomb. Here has -6 microcoulomb. Let me call this distance the distance between the negative charge and any point between C and D, x. And the distance between the positive charge, where is the problem? Oh, here. The distance between the positive charge and any point between C and D, x1. So we know that x is greater than x1. And we also know that 7 microcoulomb is greater than 2 microcoulomb. And we know that electric field is equal to K multiplied by test charge divided by distance squared. So for the negative charge, because the radius here increases, electric field decreases. And because here increases, here also increases. So it sort of cancels all the change in electric field, and that's what makes it possible for electric field to be equal to 0, because here any point between A and B, the electric field by the negative charge is obviously greater than electric field by the positive charge. A ideal emitter is used to measure the current in a resistor. Which of the following gives the resistance of a ideal emitter and the way it connects to the resistor? So a ideal emitter has a resistance of 0. otherwise it will affect the rating. And it is connected in series. If it's connected in parallel, then no current will be passing through the electrode device the emitter measures. So D is the answer. The diagram below shows a uniform electric field of strength E. The field is in a vacuum. An electron enters the field with velocity v in the direction shown. The electron is moving in the plane of the paper. The path followed by the electron will be what? So how do we do this problem? So we are asking the direction of the electron by the electric field. So force by electric field is equal to charge multiplied by electric field. And because electron has a negative charge, then the direction of electrical force will be in the opposite direction with electric field. So here will be the force, right? And here is velocity. So it will have a horizontal component and a vertical component. The horizontal component remain constant, while the vertical direction will be constantly accelerated by the force F here. So its path will be something like this. So the answer will be A. A long straight wire carries an electric current perpendicularly out of the paper. Which of the following represent the magnetic field pattern due to the current? So you should immediately know that A and B are wrong, because magnetic fields is always in a circular loop with respect to the current. So A and B are definitely not correct. And we know that current point out of the page. Now you can use your right hand to do this problem. So your thumb will represent direction of current. So point your thumb out of the page, out of the screen, and curl for the 4 other fingers, right? Curl the other fingers, and the other 4 finger will be in this direction. So the answer will be D. And also just a trick. It's not a trick, but more like a summary. Point out of the page. When current point out of the page, the B field, B field will always be counterclockwise. And when current point into the page, current magnetic field will be clockwise. Oh, sorry, here CCW is counterclockwise, right? And this is the thing you can remember. Right. And it does make sense, because counterclockwise is the positive direction and clockwise is the negative direction. And pointing out of the page is sort of like the positive direction we always use in physics, and pointing into the page is like the negative direction we often use in physics. So if currents point in the positive direction, magnetic field is also in the positive direction, which is counterclockwise. And you should know that counterclockwise is the positive direction when you are learning about torque. Okay. The diagram shows the magnetic field surrounding two current carrying wires P and Q. The wires are parallel to each other and right angles to the plane of the page. What is the direction of the electron flow in P and the direction of electron flow in Q? So here we know the direction of magnetic field. We can also know the direction of current using the same method in this problem, right? So there are two methods of solving this problem. The first method is also using your right hand. So for P method 1, let me write method 1. For P, so curl your 4 other finger in the direction of magnetic field, right? And then your thumb will represent the direction of current, which point out of the page. So current point out of the page. An electron is in the opposite direction with conventional current I. So this tells us that E flow point into the page. Right. And using the same method for Q, again curl your finger in the same direction of magnetic field, which is here. And then your thumb represents the direction of current, and your thumb will point into the page. So current will point into the page. And because conventional current is opposite to the direction of electron flow, electron will point out of the page. Right? And this will give us the answer B. Excuse me, I am a little bit sick today. So I apologize for the coughing. You can also use the second method. Here you can see that this is the what direction, clockwise or counterclockwise. This is the counterclockwise direction, which tells us current point into the page. So electron flow will be out of the page, into the page, because current is out of the page. And for Q here, this is what direction? This is the clockwise direction. B is the clockwise direction. So current will be pointing what direction? Pointing into the page. Sorry. So electron flow will point out of the page, which also give you the answer B. So two different methods. You can use either one. A lamp is connected to an electric cell, and it lies at its working voltage. The lamp is then connected to the same cell in a circuit with an ideal emitter and an ideal voltmeter, which circuit allows the lamp to light at the original brightness. So here, they're basically testing about how you should connect a voltmeter and an emitter. So ammeter. So I will make a table, not just for this problem, but for a review. So ammeter, a ideal ammeter has a resistance of 0 ohm, and a ideal voltmeter has a resistance of infinity because it doesn't want any current to pass through the device. And this should be connected in series. And this should be connected in parallel. Otherwise, no current will be passing through the device it measures, right? So just be aware of the two things listed here, and then you will be able to solve the problem. For A here, the emitter is connected in parallel to the circuit, so this will cause the current to flow in this way only, because emitter has a resistance of 0 ohm, and this is what we call a short circuit. And when voltmeter is connected in series with the circuit, right? So let me draw a diagram. If here is the lamp, because it has a resistance of infinity, the current flowing here is gonna be equal to 0 ampere, and this is what we call a open circuit. So A is wrong. B, the voltmeter is connected in parallel to the circuit. The emitter is connected in series with the circuit, so B is correct. B is correct. Let me just write this. B is the answer. C, voltmeter is connected in series with the circuit. Emitter is connected in parallel to the circuit. C is wrong. D, emitter is parallel to the circuit, so this is wrong. The diagram shows an electric circuit containing a potential meter of maximum resistance R. The potential meter is connected in series with a resistor also of resistance R. The electromotive force of the battery is 6 volt and its internal resistance is negligible. The slider on the potential meter is moved from P1 to P2, which graph shows the variation of the voltmeter V reading on the slider distance D. So how do we do this problem? So here, potential meter, when you see potential meter, you can think that the device is equivalent to 2 resistance, right? So when the potential meter is here, the circuit is this. So I'm just gonna say here is 6 volt. Here you have 3 resistors, because here the potential meter, let me write it here to save some space. Potential meter is equal to 2 resistors. So here will be P1, here will be P2, and here I'm just gonna call it X. Right. When the potential meter is here, the resistance P1X, RP1X, is gonna be equal to 0 ohm, right? It's gonna be equal to 0 ohm. So the circuit is something like this. Here is R, here will be P2, here will be X, right? And here, this resistor here is gonna be equal to 0. RP1X is equal to 0. So the voltmeter here, the voltmeter is here. I apologize for my bad drawing. The voltmeter is connected to here. And because the resistance of R sub P1X is equal to 0, they're saying that the voltmeter is connected to an electric current, which means that potential difference here is 0. So B and D are wrong, right? And when the potential meter is connected to P2, it's connected to P2. The circuit is something like this. Let me draw it here. Here is 6 volt. Right, this is 6 volt. Yeah, 6 volt. and then you have a R here, and then P1, P2 connected to a voltmeter. Right. So the potential difference by the potential difference is what? So we know that because both R and the voltmeter are gonna have a potential difference here. So we know that VR, V sub R, plus V potential meter. I'm just gonna write this to represent the potential difference by the potential meter is gonna be equal to 6 volt, right? And both of them are non-zero, which means that the potential difference by the potential meter is equal to 6 volt minus potential difference by the resistor, and this is clearly less than 6 volt. So A is not correct, and C is correct, because the potential difference by the potential meter gotta be smaller than 6 volt.